right, let's do this. So, as a reminder, this particular chapter is ethers and epoxides. Last chapter we talked about alcohols. We said that ethers also are oxygen-containing functional groups, but they're flanked on either side by carbon atoms. And then epoxides, which is really going to be our discussion of today, is technically an ether, but we put it in its own separate functional group category because they turned out to be way more reactive than all the other ethers in the world. All right, so that's what we're going to talk about today, epoxides. All right, so epoxides are ethers, but necessarily that are forced into three-membered rings. So our simplest epoxide here would just be 2 carbons and an oxygen. All right, but anything that contains that little triangle with the oxygen point is an epoxide. So if it has more than 3 carbons, all right, as long as it has that little triangle with the oxygen point, that is an epoxide. So these are both examples of epoxides here. All right, I know everybody's going to be really disappointed, but we're not going to talk about nomenclature of epoxides because, frankly, there's 2 different schemes out there, and they're both kind of a pain in the butt. So we're just going to gloss over epoxide nomenclature and go right into the reactions of epoxides. What's up?
So when epoxides form, the other bond is going to be a straight line, almost like as if it was a tertiary angle?
Say that one more time?
Yeah, like, so it's going to be always, like, straight, like, that carbon bond just going to...
You mean this right here?
Yeah, like, is that always the case?
Yeah, you'll see that typically because all I did was I drew my regular carbon backbone, and then I said, all right, this one has this triangle on it. But it is not quite as strict of a rule. So I guess to be clear, I could have drawn this same molecule and then had this single bond pointing up or something like that. That's perfectly legal as well. It's not the same strict rule that we had with alkynes. Cool. All right, so again, technically ethers, but we consider them to be different, their own category of functional group. And again, that's because they're very reactive. So why is that? All right, so epoxides, let's just kind of focus in on this little triangle here. Does anybody remember from general chemistry the type of bond angle that carbon likes to have? 109.5. Yes, exactly. That tetrahedral geometry of a carbon atom will lead to a bond angle of 109.5. All right, so carbon likes to have a bond angle of 109.5 degrees. All right, in our epoxide, does anybody remember from geometry class, what is the bond angle of a triangle, an equilateral triangle? 360. Awesome, yes, 60 degrees, exactly. All right, so in epoxides, carbon's bond angle is only 60 degrees. Right? Meaning this angle right here in my little triangle is 60 degrees. All right? So the bottom line is carbon's mad. Okay? Carbon wants to have a much wider bond angle. We're forcing it into this little triangle here, and this leads to what's called angle strain. All right, angle strain is an increase in energy due to that non-ideal bond angle. All right, and angle strain is going to help explain why epoxides are so reactive. Right? We made this ether, which is normally a very boring functional group, a way higher energy molecule because we took these carbon atoms and we bent them in such a way that they don't want to be bent. Right? So this little triangle right here is really mad. And what we're going to see in all of our reactions of epoxides, this little triangle pops open. All right? These are what are called ring opening reactions. All right, so let's talk about our reactions of epoxides. Okay, and these are all going to have this same feature in common. These are ring opening reactions. All right, so that's a little helpful phrase to keep in mind as to what we're going to expect to see. These are all technically nucleophilic addition reactions. We're going to take our epoxide. And we're going to react it with some nucleophile. We're just going to kind of leave this as generic nucleophile for right now. All right, nucleophiles are what? Electron rich or electron poor? All right, they're the things that want other positively charged nuclei. So what does that mean? They have a lot of electrons or a few electrons? They have a lot of electrons. That's why they want something positively charged. All right, so what's going to happen is if we look at our epoxide here, we have this polar bond. Our oxygen's got a whole bunch of partial negative charge. And that carbon atom has a whole bunch of partial positive charge. And so what happens is that nucleophile is going to attack that carbon, but it's not going to stop there. One of the reasons why this carbon is so willing to accept that pair of electrons, because it won't break its octet rule, is it's going to give up this pair to that oxygen. All right, and so what we're going to see here is our nucleophile gets added. We have a nucleophilic addition reaction. All right, but that epoxide oxygen doesn't just go flying off into space. It's still attached to my other carbon atom. And that will become an alcohol group, a hydroxyl group. All right, so to just keep my carbon coloring consistent here, my nucleophile is added to that blue carbon. Exactly one carbon away is now that epoxide oxygen. All right, and this is going to be a really important feature of these epoxide reactions. You are always going to have the nucleophile added 2 carbons away from where that hydroxyl group is. All right, never on the same carbon, always just exactly 1 carbon next door. All right, so let's just note, nucleophile added. 2 carbons away from that hydroxyl group, from that OH group. All right. Cool. All right, so let's just keep our simple epoxide here. Let's look at a specific nucleophile. All right, everybody take a second. See if you can't give me the product of this reaction here. So my nucleophile gets added exactly 2 carbons away from where that OH group is. In this case, this was a negatively charged nucleophile. All right. We've seen this before here. We don't necessarily have to use a negatively charged nucleophile. We can also use a neutral nucleophile. All right, everybody take a second, see if you can't give me the product of this reaction here. My product of this reaction is the exact same because remember, our neutral nucleophiles, they lose a hydrogen when added. All right, we talked about this back when we were talking about our alkyl halides. We had our weak nucleophiles, our neutral nucleophiles that we could use, but anytime we add them on, we got to take away a hydrogen so we don't end up breaking the octet rule of that nucleophile. Okay, so we're going to see the same thing here. Negatively charged nucleophiles, just attach them, right? Neutral nucleophiles, you're going to have to take away one of those hydrogens when you draw your product. Cool. All right, so let's talk about our nucleophiles that we can use here. And what we're going to do is we're going to have to take the world of nucleophiles and we're going to divide them up into 2 categories here. All right? We're first going to talk about what are called our basic nucleophiles. All right, which are just quite simply nucleophiles that can exist in a basic solution. All right, and we'll put these into different bins based on the actual nucleophilic site. So we got a bunch of basic nucleophiles where oxygen is our nucleophilic site. Kind of the simplest one would be that hydroxide ion. right, any oxygen with a negative charge, so it can also be one of those alkoxide ions, those deprotonated alcohols. That would also be a nice, good, basic nucleophile. Nitrogen is also a good nucleophilic site. Okay, so if we have a nitrogen with a negative charge, good base, good nucleophile. All right, likewise, it doesn't have to just be so teeny tiny. We can also have some carbons on there. Another one, like what we just saw, is our sulfur nucleophiles. All right, and then the last category, which is way more rare, kind of only one special case. We have these cyanide ions. Carbon really does not like to have a negative charge. You can get away with it if you triple bond it to one very electronegative element, a nitrogen. That cyanide ion is also a good basic nucleophile. All right, or rather a nucleophile that you can have under basic conditions. What do every single one of these nucleophiles have in common here? The negative charge. All right, boom. So basic nucleophiles, again, they exist in basic solutions. We can see these all have negative charges. All right, there's one more that we have to add to this list that kind of bucks this trend right here about having negative charges, and that is that MGBR business. What do we call that thing? It's named after some dude with a weird G name. A Grignard reagent, all right? So that is also a basic nucleophile. It's our one basic nucleophile that does not have this negative charge written in it here. So we're just going to make a note, give it a little special asterisk. This is a basic nucleophile, or basic conditions nucleophile. Even though it doesn't have a negative charge. Cool. All right, so this is going to be important. Basically, when we're given a reaction of epoxides, the first thing that we're going to have to do is look at the nucleophile and identify whether it's basic or our next category here of acidic condition nucleophiles. All right, these are the ones that will exist in acidic conditions. All right, we're going to see a lot of the same nucleophilic sites. We can have oxygen as a nucleophile under acidic conditions. But what's the difference between our oxygen nucleophiles under acidic conditions versus basic conditions?
Extra hydrogen.
Yeah, they're extra hydrogen. So instead of having a negative charge, they're just neutral. All right, so, and what we'll see is, remember, nucleophiles have to be electron rich. So they can't have a positive charge. Otherwise, they're not electron rich. But they can be neutral as long as they have their lone pairs on them. Then they can still be nucleophiles here. All right, so these are our neutral nucleophiles. And exactly, all I did was I took that basic nucleophile of a hydroxide ion and I added an extra hydrogen to it. I took that alkoxide ion and just added an extra hydrogen to it. All right, so see if you can't give me, based on our previous examples, an example of a nitrogen and sulfur nucleophile that we could have under acidic conditions. All right, so all I did was take my basic condition nitrogen nucleophiles, I added one more hydrogen, I took away one lone pair as well, right, because I can't break my octet rule of these nucleophiles. All right, same thing with sulfur. Instead of being HS with the minus charge, it's H2S. Or my thiol. All right, so again, the first step that we're going to have to go through when we're talking about reactions of epoxides, let's look at these two previous examples that we did, is we're going to have to classify them as being either under acidic or basic conditions. So that first example that we did was which one? That was our basic conditions, because my nucleophile has a negative charge. And what about the second example? Acidic conditions, because I have that neutral nucleophile. All right, in this case, I only had one possible product because I was using that teeny tiny symmetric epoxide, but this is going to be an important first step when we start talking about these reactions. All right. Now, I do got to complicate things a little bit here. There is one category of acidic nucleophiles that buck our trend of being always neutral, and that is our halide ions. Hydrochloric acid, hydrobromic acid, hydroiodic acid. Why are these such good acids? Why are they so willing to give up those protons? Because those halide ions are just super stable all by themselves. They don't care about having a negative charge whatsoever. So our chloride ion, our bromide ion, and our iodide ion are also good acidic condition nucleophiles, right? They have this negative charge, so they're great nucleophiles, but unlike all of our other negatively charged nucleophiles, they can actually exist in acidic solution, all right? And by that, what the heck do I mean by that? Like, what's going to happen when I put hydroxide into an acidic solution? it's just going to react and form water, right? So in acidic solution with a bunch of protons floating around, all of these negative charges are just going to bind to one of those hydrogen ions. The halogens won't do that. They're fine with their negative charge. They don't need to be, have a hydrogen on there to be stable. Cool. All right, so let's first look at our basic condition reactions here. Our basic conditions, epoxide reactions. All right, so again, just for the sake of practice, we're going to do our very simplest epoxide. I'm going to pick one of those basic condition nucleophiles. Everybody take a second and give me the reaction here. Give me the product of this reaction, rather. All right, so again, I'm going to kind of color these carbons here so we can keep track of who's who. I'll make one of them blue and one of them green. All right, importantly, that nucleophile is going to get attached to one of them. Got to make sure I add those 3 carbons on there. And if my nucleophile got attached to that blue carbon, what's going to be on that green carbon? An OH group. I will say that there's a little bit more to the story that I'm not telling you all and that you don't have to worry about as to why I keep on adding them on like opposite sides. For the purposes of this class, if you drew them both on the same side, by that I mean OH up here, and then this thing up here, that's fine. All right, there is kind of more details, more to the story that I'm not telling, which is why I always draw them on the opposite side, but for the purposes of this class, it doesn't really matter. Cool? All right. So that's all well and good, because in this case, whether I picked the green or the blue carbon, I would have gotten the exact same product. All right, but let's use a little bit more complicated of an epoxide here. Something that's got a few more carbons going on. All right, and again, we'll pick one of our neutral, or rather one of our negatively charged nucleophiles here. Let's do that cyanide ion. well now if I color these two carbons, one of them blue and one of them green, I would get a different product depending on where I attached that nucleophile, right? So now we got two different options here. All right, on the one hand, I can attach it onto that blue carbon. And then that OH group would be on my green carbon. Or I could swap them. I could have my nucleophile on that green carbon. And my OH group on the blue carbon. All right, so first of all, one thing that I want to point out in terms of the way I wanted to do this particular nucleophile because it's kind of the trickiest here. First of all, it's got that triple bond, so remember I'm going to draw that linearly about that carbon in the middle. The other thing that I want to note is this carbon, right? I actually have one extra carbon in my products than what I started with in my epoxide because that's what ends up getting attached. Remember, everybody likes to forget that there is a carbon at the other end of this triple bond here. So let's just make note, we're not going to forget that that's there. Okay, so I got two possible products here, and I'm going to tell you only one of these are actually formed here. All right, so let's try to figure out which one would be which here. If I went the blue route, that means that my nucleophile were to attack that blue carbon here, right? That's how I would get that top product. And if I went the other route, my nucleophile would attack that green carbon. That's how I got that second product there. All right, so which one of these is going to be more likely? All right. Well, how many other carbon atoms is that blue carbon bound to? Only one, so we would call that a primary carbon. And what about that green carbon? How many other carbons is that one bound to? Two, so we would call that a secondary carbon. So what do we think? Is our nucleophile going to attack the primary carbon or the secondary carbon? Primary, and why is that? More accessible, right? It's the same argument we've been using kind of over and over and over again. Nucleophiles have a much easier time getting to more accessible carbons. And so that's why we're not going to see any of this product down here. All right, so our nucleophile is going to attack that more accessible carbon. All right, so under basic conditions for our epoxide reactions, we can just kind of very simply say that our primary carbons are favored over secondary carbons, are favored over tertiary carbons in terms of where that nucleophile attacks. All right, so let's just do another example here. What's another new? Let's do one of our nitrogen nucleophiles. So we have a complete list in our notes here. All right, everybody take a second and give me the product of this reaction here. All right, so I'm going to color these blue and green. Whoops. All right, I'm going to go over to my product side. I'm going to draw those same two carbons, and I'm going to again color them blue and green. Which one should I be attaching my nucleophile to, blue or green? Green, because green is a secondary carbon, whereas blue is a tertiary carbon. So I'm going to put that nitrogen on my green carbon. I need to make sure to include that hydrogen and those two carbons. And so if the nucleophile is on my green carbon, what's going to go on the blue carbon? The OH. Cool. Now I'm obviously not done. I need to put in all the rest of the carbons here. That green carbon was bound to one other methyl group. And that blue carbon, I'm going to have to put two methyl groups on. Yeah, you can put the hydrogen anywhere you want as long as it's on that nitrogen.
Let's just remove it when you're adding.
It's a negative nucleophile, not a neutral nucleophile. Cool. Okay, and we get some big ugly products on the other side here, but importantly, again, we always see that our nucleophile is added 1-2 carbons away from that hydroxyl group. And importantly, we have this ring opening reaction, right? We have a ring on our reactant side, it opened up, so we don't have a ring anymore on our product side. Cool. All right, so now we got to talk about our acidic conditions epoxide reactions. All right, right? These are a little different because under acidic conditions, the epoxide oxygen gets protonated. All right, so what do I mean by that? I mean, if we took our epoxide and we stick this thing in a acidic solution, that acid proton is going to attach itself to that oxygen, giving it this positive formal charge here. All right, remember we said acids, just by definition, are proton donors, but that sounds like this nice, neat, agreeable process. Really, they're just sticking protons anywhere they can. So if you put an epoxide in a solution of strong acid, that acid's going to stick a proton onto that oxygen. And that has the effect of making these carbons right here even better electrophiles. Oxygen, being so electronegative, is all pissed off to have that positive charge, and it starts pulling at that pair of electrons in that carbon-oxygen bond even more forcefully. All right, so that carbon is left relatively electron deficient, meaning it's an even better electrophile. All right, we can just say oxygen pulls electron density even stronger. So under acidic conditions, we can get away with using these nucleophiles. Remember, these would have all fallen under that category. At least most of them would have fallen under that category of a weak nucleophile, right? Well, how can we get away with using such a weak nucleophile? Because under acidic conditions, we make our electrophile that much better. Okay? Cool, but this has this sort of unforeseen consequence, or I don't know if that's the right way to say it, but anyway, it has a consequence here, which is specifically for if we have tertiary carbons under acidic conditions. Right? If we take a tertiary epoxide, or rather an epoxide that contains a tertiary carbon, and we put it under acidic conditions, we're again going to see the same thing that we saw before, where we protonate that oxygen. All right. And again, now this oxygen, being all mad that it's got this positive charge, it starts pulling electron density away from those carbon atoms. But it turns out that it's much better at pulling electron density away from this tertiary carbon over here. So what happens is it actually starts to break this bond here before the nucleophile even arrives. All right, so when this bond is protonated, because this is a tertiary carbon, the oxygen-carbon bond starts to break. All right, so really this drawing here is kind of a little misleading. You'll often see these transition states drawn instead like this, where this bond over here is already half broken. Okay? So because of this, under acidic conditions, specifically if we have a tertiary carbon, that is going to be the one that's attacked first. All right, so under acidic conditions, tertiary carbons are preferred. If it's not a tertiary carbon, then you just go to your more accessible argument. So it actually goes tertiary, then primary, then secondary in terms of our nucleophilic attack. Okay? Cool. So again, when we see an epoxide reaction, the first thing that we're going to do is classify that nucleophile as either an acidic nucleophile or a basic nucleophile. All right? And why is that? Because it turns out that under basic conditions, we have a different preference from what our nucleophile attacks. It's just this simple accessibility argument where primary is preferred over secondary, is preferred over tertiary. But under acidic conditions, we have this really weird phenomenon going on where if we specifically have a tertiary carbon, that bond already starts to break before the nucleophile even shows up on the scene here. All right, so under acidic conditions, we have a different preference for our what we call regioselectivity here, where tertiary carbon is preferred. And then it just goes to our accessibility argument where it's primary followed by secondary. All right, so let's just kind of summarize here. That's not how you spell that. Epoxide reaction, what's called regioselectivity. Under basic conditions, the nucleophilic attack will be primary, then secondary, then tertiary, all right, and again, this is all because of that accessibility argument. Under acidic conditions, when we're talking about our nucleophilic attack, it's actually the tertiary carbon that's preferred first. And again, this is because of that weird transition state. With that half broken bond. If there's no tertiary carbon though, then you don't have to worry about it at all. And it's just that regular old accessibility argument. All right. Cool. All right, so let's do some examples here. We're going to take an epoxide. I'm going to put it in the middle. Because on the left-hand side, I'm going to react it with a basic nucleophile, and on the right-hand side, I'm going to react it with an acidic nucleophile. All right, so we'll use let's do our thiol over here, a neutral nucleophile. And over here, we'll do that same molecule, but the basic version where I take away a hydrogen. And then we'll do another example. If you guys get that one, you can move on here to do this next example. All right, let's take these examples one at a time here. I'm going to play the same game where I'm going to look at my epoxide and say, all right, you're blue, you're green here. All right. Under basic conditions, which one of these is going to be attacked? Blue or green? Green, right? Okay, so cool. We got a secondary blue carbon, a primary green carbon, and remember, under basic conditions, primary is preferred over secondary, preferred over tertiary. So absolutely, I'm going to get my nucleophile added to that green carbon. All right, so when I draw my product here, okay, I'm going to start by drawing that blue and that green carbon. And I'm going to say, all right, my nucleophile got added to the green one. So here's my S with those two carbons. And what do I need to put on the blue carbon? The OH. Right? So by starting with those are the two that kind of changed in this reaction here, right? So I put my two functional groups on those two carbons, and then I just need to make sure to include the 1, 2, 3 other carbons that were in my reactant to begin with. So 1, 2, 3. Right? And as always, how can I double check my product here? Count carbons, right? So I'm just going to go through and double check 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay? But I start with those two epoxide carbons and then attach what needs to be attached. All right, so if we go over to our acidic conditions now, where am I going to put my nucleophile? The blue carbon or the green carbon? Again, the green carbon, right? Because neither of these are a tertiary carbon. Yes, under acidic conditions, tertiary is preferred. But then, if there's no tertiary carbon, it's just primary followed by secondary. So just like before, I'm going to draw my two carbons. One of them's green, one of them's blue, because I'm comparing a primary and a secondary. There's no tertiary in there. My nucleophile is going to be attached to that primary carbon. And because I have a neutral nucleophile, what am I going to make sure to do when I attach it? Get rid of that hydrogen, right? So it's not going to be SH that's attached, but just S. All right, again, and especially for acidic conditions, because these are where we're going to see our neutral nucleophiles, we're going to remind ourselves that neutral nucleophiles lose hydrogens. All right, obviously I'm not done. I got to put my hydroxyl group on that blue carbon. And I got to include all those orange carbons. I had 3 of them, so 1, 2, 3. And I can double check by counting my carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right, so what was the difference between my products here? There's no difference. All right, in both cases, whether I carried this reaction out under basic conditions with my sulfide ion here, or whether I did it under acidic conditions with my thiol, I'd get the exact same product. Let's play that same game over here. Again, one of these is going to be blue. One of these is going to be green. Under basic conditions, where am I going to put that nucleophile? The blue carbon, because blue's secondary and green's tertiary. And under basic conditions, it's just always an accessibility argument. So I'm going to draw my 2 carbons. Whoops. All right, color 1 blue and 1 green. If my blue carbon gets that nucleophile, then I need to put what on that green carbon? That OH group. And then I'm done? No, I just got to include all the other carbons here, right? So that green carbon had these 2 methyl groups. Stick those on there. My blue carbon, I'm going to need to put 2 more, an ethyl group on there. 1, 2. Okay, and then again, we can always count carbons to double check. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, so given what we just discussed and our kind of practice at drawing these products, if you have not already, take a second and see if you can't give me the product of this acidic condition reaction with this alcohol now. All right, so our acidic condition nucleophile, I'm going to draw in my green carbon and my blue carbon. And where am I going to put that nucleophile? On the green carbon, right? So now we have a tertiary carbon under acidic conditions. This is kind of like our asterisk little oddball set of conditions here where we see something different. Now we're going to attach that nucleophile onto that tertiary carbon. And I'm going to make sure, because this is a neutral nucleophile, that it loses that hydrogen in the process. And if my nucleophile goes on the green carbon, what's going to go on the blue carbon? The OH group. And again, just like before, I need to include those 2 methyl groups on the green carbon and that ethyl group on the blue carbon. I'm going to be good with my lone pairs too. So now do we see a difference between our acidic and basic conditions? Yes, because we have a tertiary carbon on that epoxide, right? If there's no tertiary carbon, you're going to get the same product regardless of which conditions you use. However, if you do have a tertiary carbon, that's going to be preferred under acidic conditions. Cool. One more thing, on your end of the week assignment, I botched it and I put these substitution of alcohol questions on there that we never went over. We talked about elimination of alcohols, which was missing from that assignment. So that was my bad. I included the one group and forgot the other group. I just dropped those questions from the assignment, so everybody got their credit for those questions. And then just remember that there are those elimination reactions, those dehydration reactions that weren't featured on that end of the week assignment, but you did have that practice assignment, your lecture assignment. Just don't forget those are a part of our alcohols chapter. All right, cool. All right, enjoy your weekend.
those questions, I was like tripping.
The substitution? Yeah, that was
I
my bad.
like looking
That
at
was
them.
totally just not something we talked about
Once I
even a
saw
little
them, I was like, We
bit.
did not talk about it.
We did not talk about it even a little bit. No, and then I forgot. So we did. Yeah, we did the wrong one. That was my bad. But yeah, they're missing now, so you just got your points.
Thank you.
It's like not even admit that.
Yeah, well, I mean, good call.
And then, so for this one, they're supposed to be.
There's the dots, yeah.
Okay, cool. I just assumed.
Yeah.
Thank you.
I got lazy and didn't include my load and pairs. Thank you.
Have a good day.
Yeah, you